Thank you. Okay. So let's start. So, good evening, everyone. I'm Archita. I'm a PMRF scholar at ISER Kolkata. This is a week 4 assignment class, interactive session for the NPTEL course, Air Pollution and Control. I could not take the Monday session due to some emergency, so I am taking it today. Now, in the previous week 3 lecture, someone asked me that they are unable to understand the equations and the derivations. So, and I have seen other TAs, they have like gone through a lot of what do you say, lot of queries regarding like numerical problems for the same. So what I decided is that I will try and make you understand different Gaussian plume model for both for point source, line source, and area source. And then there are few questions that we'll deal with, like few uh, normal questions that we will see. And I personally, I am not good with maths, but I will try to explain as much as possible. Okay, so let's start. So first, we'll go. In the previous lectures, we have seen that whenever we talk about air quality monitoring, we take three sources. One is point source, where we know that the emission is from a point. Then next is line source, where we think that emission is across a line. For example, traffic. So traffic pollution is along a line. And then third is area source, where it is for a large area. For example, uh, um, during October November there is lot of uh, agriculture residue burning in Punjab and Haryana, right? They burn their whatever is left from the after the harvesting, whatever is left they burn. So that comes under area source emission of air pollutant emission. So for each of these different sources, that is point, line, and area, there is different technique to measure the amount of pollution that it is creating. Okay, so it we will start with the uh, point source, and then we'll go ahead and see how the derivation of line source comes. Okay, now this is a simple diagram of a stack. For so this is stack of height h, uh, hs, and then this h is the del h is the height that a plume can has risen. Capital H is the total height, and z is the direction of buoyancy. And then this is the plume center line, this is the x direction. And then these are y and z direct, this is y perpendicular, and this is z direction. So this is how trajectory of plume is shown. Now to calculate that, like to comment on how the plume will behave for this point source, which is the emission that is coming from this chimney, we devise a simple method that, let's say, this square is the plume. This is one, this 1 by 1 cube is a very tiny area of the point from where the emission is happening. Okay, so when we decided in a 3D space, we know that it will have three direction. X is the direction where plume is moving, y is perpendicular, and z is the direction of buoyancy. Like when when the pressure occur from the bottom, the plume will rise in the z direction. So these are the three different direction, and similarly in each direction there will be a plane. So there will be an xy plane, which is the dx. Okay, so these okay, so there are three different plane: xy, xz, yz, all of them. And in each plane there will be some displacement, right? So this is displacement dy, displacement dx, and displacement dz. So these are the displacement of air in that particular point, and here we are considering point as a cube. Okay, now first we calculate the net rate of bulk motion, that when the emission is happening from this chimney, and let's say we consider a point which is in the form of cube, then how much uh, the emission is going into this area or this point, and how much emission is coming out of this area. Okay, that will be the bulk motion of pollutant, yeah, or of emission. So to calculate it, uh, we find that how much is going in and how much is coming out of this area, which is this cube. Now to calculate that how much pollutant is going in or how much emission is going in, what we need is we need to know that what is the concentration of the pollutant. Okay, then this pollutant is also affected by the wind speed, so we need wind speed, which is du, right? Now these two parameters are there. What is left is area. So if you see that, so look at this cube. If we say that from this direction there is a movement from this direction, then it is lying on this plane. And for this plane, if it's a cube, okay, let's say it's not a cube, if it's a cube, it is side square, area is side square. If it is a rectangle, it is length into breadth or breadth into height. So similarly for this plane, the area would be dy and this is dz, right? So if just a second. Okay, so if a particle is moving in x direction, then it is contacting this point or this area on two planes. On this plane where length is dy and breadth is dz. So therefore what the emission that is coming, that will be concentration into wind speed into area, which is dy and dz, right? So this will be the influx of emission, which is written here. Now once the emission act on this point, which is in the form of cube, there will be something that will come out of it. So now to find it, out will be in, that is whatever has already entered into the system, plus some amount. So what is that amount? That will be this region. So this region is dx, right? And so what we add to it is that how much displacement the emission will have on for this region. To calculate, so what we write is same as this du, oh sorry, cu dyz. Just a second. So what we write is, so this will be same. Now on this emission that is coming, there will be a component dx, which is the displacement along the x direction. So we write change in concentration, which is cu dy dz, due to displacement in direction of dx, and that will be this, which is out. So what we include in out is whatever has entered plus the displacement in the dx direction because of, or the effect of dx direction on the emission that has entered into the area, into the point. Okay, so this will be the uh, final term or the rate, out rate for bulk motion. And when we subtract to understand what is the net movement inside this square, okay, all we need to know is that what is or how much the emission or the pollution is behaving on this particular area. Let's say it's a 1 by 1 area. So how much emission is affecting this 1 by 1 cube, and that will be you subtracted, and the answer will be displacement or the change cu dx dy dz. In the lecture that sir have shown, sir have used as it as a area. Okay, but here in this so I have taken this from this atmospheric dispersion lectures. If you want, I can give this to you in next class. So this they have done. Now this is for one direction dx. Now you do it for all the direction, because if you know that, let's say if it's a smoke, okay, it will move in all the direction. So currently what we calculated is that how much the emission is moving in this direction. We measure it in dz direction, and we measure it in dy direction. And so similarly it will be same for everyone. So here I will write. So if I change it a bit, it will be, for x it will be this. Just a second. So for x direction, dy dz would be area on the yz plane, which is this plane, and you take cu and then dx. And what sir has done is, sir have multiplied this and is written change in concentration u, and sir has written it as volume. ठीक है? Okay, and this will be the for x. Now if I write for y, it will be change. Ideally it will be like this. Okay, and for z it will be okay, sorry, yeah, there is y here, because we are, the change is with respect to y, and here the change is with respect to z. So if we write for y and z, we write it like this, similar to x. But now there is a catch. The catch is that whatever we have written, we have taken only one thing in, which is advection, where advection or advection flux. So when we take advection or advection flux in consideration, we are completely ignoring another phenomena, which is diffusion. And the difference between both is, advection means that there is only bulk motion. Okay, so if whatever is coming, it is moving in only one direction. Diffusion means that there is dispersion in other direction as well. So ideally we have to include a component to each of these, which is known as dispersion flux, which is dx, dy or dz. Okay, if I include dispersion flux in all three, the equation becomes this. So what we did is that okay, before that, here they have written that, it's written that what is the net rate of motion. Now if I need to find the concentration, change in concentration, then we can write the change in concentration with respect to time multiplied by displacement in all three direction, right? And if I use this and these three equations which we have written here, the final equation would be like this. What they did is, they have taken the advection flux for x, and then they have added the diffusion in all three direction. So these three are diffusion flux component for x, y and z. Okay, so ideally this would be the equation, that you are taking that in x, because that will be the plume direction. Only advection, which is the bulk motion of particle, is happening. And in other direction, also including x, diffusion is also playing an important role. But if you have read the lectures, you understand that one of the assumption that was taken was that there is no diffusion in x direction. Okay, it means that there is no diffusion from the line of movement of एक second. Yes. Okay, just a minute. Hmm. Is it clear now? Okay. So what I'm saying is that the rate of change of concentration with respect to time depends on advection flux, that is bulk motion in x direction, and then diffusion in all three direction, because x is the direction of motion, right, of flume. So there will be bulk motion in x, but in other direction, what we are saying is that there will be diffusion due to turbulence. Okay, but what sir, in the lectures it was said that what if we assume that there is no diffusion in x direction, that is in the direction of motion there is no diffusion happening. What will happen? This will cancel out. Okay, so this whole term becomes zero. Now another assumption that was taken is that the state is the environment is in the steady state. In steady state, there will be no change in the concentration with respect to time for that particular point. If I do that, then dc by dt also becomes zero. So this term is also gone. Now if I rearrange, it will look something like this, which is this will go here. So u change in c with respect to dx is equals to dy c square del square c del y square plus dz del square c plus dz square. That is, so what this term signifies is that the change in concentration in the direction of plume will depend on the diffusion in both the direction. Okay, and speed. So you need to understand what are the components that could be affecting the plume, the concentration of plume at a particular point source. Okay, and then what they did is they did its partial differential, second order partial differential. They solve it and they come up with this. Now I have tried it. I don't know how they solve it. I have checked out, like I have checked out papers also, but I could not understand that how by second order partial differential equation this equation has come. I will check again if I find something and I will let you know. But so far, this is the, after this they did this second order partial differential equation and they come up with this term, and then they solve it for now what this x is a constant that depend on the boundary condition. Now what they did is they try to find that, to calculate x, for that they need a they do this emission, calculated the emission rate, which is q. So q is, so if you know that emission at any particular point will depend on same, it's same as if you see the what I wrote for the x, which is concentration, speed, change in the yz plane. Okay, now why they have taken only yz? Because we are seeing emission in the direction of plume only. Okay, we are not seeing in any other direction. And then they integrated to find the value of q, double integrated. Okay, sorry, they put the value of c from this equation and then they solve it by integration to find value of k. And Okay, so this is k, and then they put this k value again to this equation, this boundary condition value to this equation, and solve it to find this. So ideally this is the concentration of a plume at a point source. It depends on emission rate, diffusion flux, and speed. Okay, now what they did is they also find this sigma y and sigma z. Now sigma y and sigma z are dispersion coefficient, that is that how much the particle or the emission is dispersing in these direction. Okay, so in dispersion coefficient, all you need is how much there is diffusion there is, and xu is constant. Okay, because what we are seeing is that if a plume is moving in x direction with a certain speed, then how much it will disperse in the y direction. So it depends on the how much diffusion there is in the y direction. So that is how they calculated sigma y and sigma z, where x by u is constant. Now for this they have this in the last class I said that there is one table that was followed, which is the I think Pausely Gifford table, and that is these plots he has given, from where you can have a sigma y value, and you can find x, and you can have x and you can find the sigma y or sigma z value. So these are to understand the to find the horizontal and the vertical dispersion values. That is one thing. So you put the dy and dz, you replace with sigma y and sigma z values, and so if you write it, is it becomes sigma y square divided by 4x, and that will be u, right? This it becomes dy, and similarly for dz it is sigma z square u upon 4x is equals to dz, and from here you put the dy and dz value in this equation, here and here. And another thing is this z. Okay, so z is this direction. Now this del h, okay, or this overall height of stack can affect the z direction, right? It can either add up to the force that is coming, so, and or either, if it's a small stack height, then z will be small. If the height of stack and the force that it is coming out is large, then the z is large. So what they did is they find two terms of z. One is z minus h, that is the height uh, in the or the diffusion in the z direction, minus the total height, which is the height of stack plus height of the plume. Okay, or either it could be z plus h. So for after solving for dy dz and z minus h and z plus h, they come to this equation, which is q upon 2 pi u sigma y and sigma z, and you take this y square by dy term out because we don't have any alternative to this, and then for z square there will be two term, one is minus h, another is plus h. Okay, and this will be the final equation to measure the how the plume is behaving on a point source. Okay, now let's move toward the line source. Now for line source, again uh, there will be assumption. First assumption is we are taking the line source that are at ground level. Okay, if we take line source at ground level, then if we take line just one second, if we take line source at ground level, z becomes 0. Okay, that is one. Then another is that x is perpendicular, that is there in the point source x is in the direction of plume. or in the direction of wind. Here the wind direction is perpendicular, it was considered. We don't know, currently we are just saying it is perpendicular. And y is in the direction of motion of car. Okay, that is infinite length source. Now we have the point source equation. What if z becomes 0? Okay, if you put z is 0 for ground, okay, if z becomes 0 for ground level, the equation becomes like this, where this is same, only height h square by 2 sigma z square. So only height of the stack plus the height of the plume is affecting, not any diffusion or motion in the z direction. Here we need to understand that there is no z direction. So there is no diffusion in the z direction. There is only x direction which is perpendicular, y direction which is along the plane, and the only the height up to which the plume will rise. Okay, this height which is h matters. So then we comes to this equation, but now let's solve it. Okay, so for solution, what, okay, just a second, it's the line source. Okay, so what sir said is that let's say you consider a patch in the direction of motion which is dy, a rectangular patch which has a displacement or a distance of dy. Okay, small strip with dy. Now if I have to calculate q here, which is the emission rate, it depends on the mass, which is the mass of plume, and how much it's traveling this distance in a particular time. Okay, so how you write it is that it depends on okay, so we find this term which is small q, which is mass, how much mass of emission or plume is there or pollutant is emitting per unit time, per unit length, and the emission is in the direction of dy. So q is dy by dy into q, and you take this, you put it in the first equation. That is one thing. Now you integrate it, and after integration, so before, okay, so we have to integrate it here, right? But we need to see that what are the terms that will not be that are independent. Okay, for example, dy and dz are independent because, sorry, not dy, sigma y and sigma z are independent because they are what, they are dependent on dy, x and u, right? Or they are dependent on dz, x and u. So sigma y and sigma z are independent of change in concentration in the direction of y. Okay, also h is independent because h depends on sigma z. So that is also a we will take all of these out, and we will integrate only what, change in the direction of motion of car or change in the direction of motion. So we integrate y square 2 sigma y square with respect to dy, and always the integration is from minus infinity to plus infinity. And okay, this, okay, and if we do it just, yeah, so that is one thing. Now what they did is they take all this entire term and put it as a constant k for now. Okay, they are saying we'll deal with this term altogether later, let keep it k, and it's minus infinity to plus infinity, this entire term which depends on dy, and dy is the strip which we considered in the direction of motion of car or any vehicle. Now again they find another term. They put another term which is s, and what they did is s is y upon sigma y root 2. Okay, now the reason they have used that term I will explain in a bit. So they use this term. Now if I differentiate, so ds is equals to dy by root 2 sigma y, and the value of dy is root 2 sigma y ds. Okay, just a sec. Okay, now what you have to do now, the reason they have taken this term is comes here. You put the value of y upon you put the dy value here. Okay, so c is equals to k minus infinity to plus infinity exponential minus, now y square upon, if I square it, okay, so what it turns out, s square is equals to y square upon में sigma y square into 2, because root 2 square is 2, so this entire term is s square, so they put minus s square, and dy is what, dy is root 2 sigma y ds. Okay, now these terms will not be affected by ds, so they put it aside, so it is root 2 k sigma y, and you integrate s from minus infinity to plus infinity, you integrate minus s square. Okay, so your answer would be this, which is root pi if you integrate, and then this k is this constant, right? You put the value of constant, and your final equation to measure the concentration of a line source will be this, which is 2q root 2 pi. Now why it is root 2, they just remove this, so if it is root 2 square, okay, if I write 2 above, then this thing will be like what you say, removed or resolved. Okay, that is why there is 2q, and below there is root 2 pi, because they have to resolve these terms, and this is the final equation. But remember, this equation is for perpendicular wind direction, that is dy is perpendicular in the direction of motion. Now they are saying that what if I am saying that the wind is moving, or wind is acting at a direction with an angle phi in the sorry, not dy, the x is at an angle, not perpendicular. So in that case, so it is acting in the at an angle phi with y. Okay, so here one more term they have included, which is sine phi, to resolve this conflict that wind can have any direction which is near which is within the range of 20 degree, okay, like above 20 degree. So that is for the line source. Now for the area source also sir has discussed. I will try and explain it in short. For area source they have used the same formula as point source. The only difference is that for an area source, what you consider is that, let's say if this is the area in which the emission is happening, okay, you consider a far point from this area, let's say at point p, and you consider that you calculate uh, the effect of emission on this far point p, and then you extrapolate it for this, sorry, for this area. So and this distance which is to this far point from the center of the emission will be, let's say, xs. Okay, and the entire length that this emission is covering is, let's say, s. So the equation was this is s by 4.2. So with this you measure how far, if you know that what is the area, what is the length covered by a particular emission source, you can find that how far you have to consider this point. Okay, based on this equation, based on this s divided by 4.2. And once you do that, all you need is, you don't have to do anything, you have to calculate the entire region it can affect. So you have to extrapolate it here, which is if the point is here, and you see that how much total area it can affect to far off point, and you measure the Gaussian plume for these point using the same equation that we have calculated for the point source. Okay, so these are the three different plume model for the line, point, and area source. And I hope I was able to uh, make you understand. If there is any doubt, you can ask me. I will try to resolve it. And now there are few questions that we can address, which are also related to the lecture of week 4. So first is that how concentration of pollutant are uh, affected by the wind. So we know that if their wind is, we have seen in this also, in this equation also, that sine theta is in the denominator, right, and theta is the wind angle. So if the wind is high, concentration is low. So the answer is that with increase in wind angle, the concentration decreases. Yes. Okay. Just this one, right? Okay. Hmm. I hope it is. You can see it. Okay. So we have seen in the line source also that sine phi is in the denominator. So the higher the wind angle, the lower will be the concentration. So they have inverse relationship. So that will be the first. Second is, what are the assumption that Gaussian plume model has taken. So far we have seen that the assumption was steady state, which is del C by del T is equals to 0. No diffusion in the x direction, so there will be no dx. Okay. Then diffusion will be molecular diffusion. Then there is continuous emission rate, that is q will be in continuous. Then they also considered flat terrain, constant wind direction, and normal distribution. Normal distribution means that plume is like this. Okay, but we have seen in previous lectures also that plume can behave differently. Okay, it can be like this, it can be almost flat, it can be like this. So plume does not behave in same way, but in this Gaussian plume model we consider that plume is normally distribution. Normal distribution means that the amount of diffusion in the x direction is equal, sorry, the amount of diffusion in y direction is equivalent to the amount of diffusion in the z direction. Okay, that is one of, that is also an assumption. And same the conical plume. So these are some of the assumption that is being taken. Now in the last, I think second last lectures are discussed about the air shed. So there can be a question which is that what do you call a geographical unit which has common characteristics of air pollution emission source? Now the answer is airshed, but I will just explain. Airshed means that, let's say you consider an area where if you measure, let's say in a area you have multiple air pollution measurement device, and the result that is coming are almost similar, and the metrology around it is also similar. So we can say that a particular region, for example, you consider a very small district in, um, let's say Rajasthan. So in that district, if we consider, we measure air pollution, and we find that the value of particulate matter, the value of gases, all of that is near about same. The meteorological condition is also not very fluctuating, then we can call it a airshed. That is a geographical unit where the pollution concentration or the pollution is almost similar. There is not much change in the pollution. Okay, that is what we call as airshed. Now, what are the methods for delineating an airshed? So that means that how do you determine that particular region? Okay, that particular region is an airshed. So to do that, we need three things, which will be discussed in the next lecture. So one is emission inventory, meteorological data, and air quality modeling. So air quality modeling can be done by the manual instruments. Okay, so for example, the NCAP or the CPCB have instruments for the measurement of gases and aerosol set up all across India. Okay, in every state there are multiple districts which has air quality modeling monitoring device, and then that is manual way. Another way is you use remote sensing, satellite data, or you use models. For example, there is WorfCam, there is other models which you can use to comment on the air quality of a particular region. Then next is meteorological data, which is nothing but what is the temperature, what is the humidity, how much is the wind speed, and what is the what is the wind speed, humidity, temperature, and if there is any rainfall. All of it comes under meteorology. Then last is emission inventory. Now emission inventory is a term which is used, so it is made of two words, right? Emission and inventory. Emission means that what is the amount that is being emitted for a particular pollutant. Okay, for example, if it's PM, how much PM is being emitted from a particular source, from a particular area, right? And inventory means a list. So what they do is generally there have been equations and models to comment that from a particular source, for example, it can be vehicle, it can be agriculture. So from a particular source, how much pollutant can be released, and how much pollutant means each pollutant. For example, from vehicle we can have NO2. Okay, we can have particulate matter, we can have carbon monoxide. From agriculture we can have for example, this aerosols, brown carbon aerosols, and other gases, PAHs, all of these. So you take different sources and you see what are the different pollutants that are emitted or released from these sources, and you see that how much they are releasing. So you make equations that if, let's say, this much vehicle are moving in a road for this much time, then they will release this particular amount of NO2, or by using a equation, or particular amount of particulate matter. So for each of these pollutant there will be an equation that will be generated and will be used in the models. Similarly, for agriculture, for cattle's for the yeah, cattle residue, all of the, for industries as well. So that is why emission inventory is like a list or a bundle of different equations that we can use to calculate the effect of each source on each particulate matter. Okay, and we can use it further for the modeling. Now last question is about the assimilative approach, assimilative capacity. Now, what is assimilative capacity? It is the amount of pollutant that can stay in the atmosphere, which is above the which can be below the threshold limit. Okay. So for example, national NNAQS, National Accreditation of Air Quality Standard, have devised a threshold for each pollutant, right? So they have devised a threshold for each pollutant, and that so assimilative capacity is that how much a pollutant can be accumulated, pollutant accumulation in the atmosphere, which is, yeah, which will be below threshold limit. Okay. So the threshold limit which is being devised by this agency or other agency, for example EPA, so in an environment, in an air shed, the concentration of each pollutant should be below these threshold, and that concentration is called assimilative capacity. That how much pollutant can be accumulated in a region or in an atmosphere, so that they will be below the threshold that is being set by the agencies. That is the assimilative capacity. Now there are two approach that are used to measure the assimilative capacity or to estimate the assimilative capacity. These two approach are ventilation coefficient and pollution potential. Now each of them has a different effect on assimilative capacity. Okay. Ventilation coefficient, as the name suggests, ventilation means that there is more diffusion. Something is going out, something is spreading. So if atmosphere has high ventilation coefficient, then the assimilative capacity is more. Okay. It means that, if let's say, so it depends on the mixed layer height, which we studied I think in last to last lecture, which is the height above, after the emission, the height till which the pollutant can stay in the atmosphere, that is mlh. So ventilation coefficient depends on the mlh and the wind speed. So if in an atmosphere is very windy and the mlh is very high, then ventilation coefficient is also high. Okay. And hence the assimilative capacity, that is the amount that can stay, will also be high, because if there is more dispersion, then the accumulation will be less, right? So more pollutant can stay in a same region if there is more ventilation. Okay. So assimilative capacity is directly proportional to ventilation coefficient. That is one. But for the pollution potential, it is inversely proportional. That means, if in an atmosphere the particle concentration increase rapidly and they are polluting, their potential to pollute. Okay. For example, some particles are have higher threshold, some particles have lower threshold. Okay. So if a particle has a higher pollution potential, ability to uh, high ability to pollute an environment, then it can retain or it can stay in the atmosphere less, and hence can have less assimilative capacity. Okay. So these two approach, both of them has an effect on the assimilative capacity or the pollution accumulation below threshold, but they affect the assimilative capacity differently. One can directly affect it. It means if ventilation coefficient is high, assimilative capacity is high. If ventilation coefficient is low, assimilative capacity is low. Other effect, inversely, it means if the pollution potential of a particular particle is high, then its capacity to retain will be less. If the pollution potential is low, the assimilative capacity is high. Okay, so this is for today. In the next lecture, lecture 5, we will discuss emission inventories and emission inventory for different source profile. If you have any questions, you can ask. Anyone wants to ask anything? Otherwise, for today, the session is over. Okay, thank you. Yeah, you guys can leave. The session is over. I will upload this video as well to the YouTube. So whoever has not joined can check out.